Good afternoon, everybody. Thanks, Giovanni, Silvia, and Monica for this kind invitation. It's an honor to be here and to show some of these recent works, and it's a pleasure. So I'm going to talk about some recent results with Benedetta Pelacci and Delia Schiera from Italy. And basically, or particularly today, on the real world case, let's say, of Choquard equation. So the general Choquard equation is minus Laplacian of u plus, and today we're going to show some results with a variable potential, v of x, u, and this non-local term with a convolution I alpha with respect to u to the p and u to the p minus 1. We're basically interested in positive solutions. And I'm going to give an overview of the Choquard equation because I don't know about the audience, how much people are acquainted to the Choquard equation. And then I'm going to talk particularly on the case we treated with p equals to 2, for example. Okay, so the general Choquard equation would be for n bigger or equal to 2 alpha between 0 and n. The convolution is realized with this Reed's potential, a alpha modulus of x to the n minus alpha. And then we treat the case where p is in this range. So the first comment I want to give is why p on this range? But before that, I'm motivated by some physical problems too. So the case we treated is with a variable potential v, and let's see how far we can go. V is going to be a positive potential, but can oscillate, can come from above, can come from below. The physics behind this equation when alpha is equal to 2, p is equal to 2, goes back to Froelich and Picard's with a model of Polaron, which is some real world problem in condensed matter physics. And I always try to learn a little bit from where the problems come from. So this is our free electrons in a ionic lattice, which interact with photons associated to deformations of the lattice. So basically the V of x that we see comes from this deformation of the lattice where photons and electrons are interacting. This was first introduced by Choquard in '76, modeling one component plasma. Lieb also worked from a real world problem, Lieb and Thomas, studying ground state energy of strong coupling polarons, and many others. Anyways, I don't know much of the physics, but I tried to learn a little bit to get motivated on the equations. The physical model is really when p and alpha are equal to 2. The Choquard equation is related to several other partial differential equations with non-local interactions. For example, when studying standing wave solutions of Hartree equation, this is the equation that comes up, and when the term of the convolution is with this sign, we say it's a Choquard focusing nonlinearity. The autonomous Choquard equation that comes from that one have been studied for many years, but mostly recently, many people are touching this and trying to get more and more information on the Choquard equations. So I cited some, but there are many others that have recent nice results on this. An interesting paper that I refer is a guide to Choquard equation by Moritz van Schachtingen, where they give an overview of the state of the art of the problem up to 2017. So for those who want to know about Choquard equation, don't know much, this is a great review paper on everything that has been done up to recently. Okay, what about this convolution potential that comes into play, and what's the role it plays? Okay, in order to have the variational formulation of this problem, the integral that is going to come up have to be defined. And it's defined depending on Hardy-Littlewood-Sobolev inequality, which is this inequality written in red. And depending on where your f is, you are going to have the integral well defined. So this gives the constraint on the p that we have, because for us, the f is going to be u to the p. And then, because of Hardy-Littlewood-Sobolev inequality, you have to have this integral term of the convolution I alpha convoluted to UP times UP. This has to be it's bounded by Hardy-Sobolev inequality, and it has to be bounded by some integral that is finite. So it gives you the range where you have to work in order to have this well defined. Because of f plugging in f equals to u to the p, we end up having that if you take u in H1, it's continuously embedded by Sobolev, continuous embedding in this Q space. And this happens even only if P is in this range. So we end up with a range where we can work Choquard equation variationally. In this case of my presentation today, I'm going to stick to the physical problem where P is equal to alpha and equals to 2. If you plug in this information, you end up with the dimensions between 2 and 6. So for my particular case, I'm going to be restricted to these dimensions. But there are other restrictions imposed by what I want to do that is going to give n between 2 and 5. But up to now, just from Hardy-Littlewood's inequality, I would be able to work between 2 and 6 dimensions. Since this is the dimension that I'm able to work, I can treat the critical points of the functional associated to the equation. So that's the action functional associated to Choquard's equation in this range where P gives the convolution term well defined. But now, going back to some works where the V is variable. So the first works go back to Pierre-Louis Lyon in 1984 when he treated a potential V of x below some limit V infinity. So in order to get critical points for the functional associated functional, it was possible because when V is below V infinity, you can apply concentration compactness. And this was one of the examples that Lyons gave in order to apply concentration compactness and get convergence of PS sequences and solutions for the variable potential problem. But it's the classical potential that comes from below. What can we say about potentials that come from above or which oscillate going to some limit V infinity? So that's the challenge. Go beyond and see, since we cannot apply directly concentration compactness, what can we do in order to get on the same spirit the solutions for the critical points for the function? Okay, when V of x approaches V infinity from above or oscillating, then higher level energy levels have to be searched. This requires a deep study of possible lack of compactness of the bounded PS sequence due to Unboundedness of the domain in Rn. So this is known, it's understood by most of people in this audience. And then we have to search for bound states at higher levels in versions of the splitting lemma introduced by Struve when trying to understand what is going to happen to a Pallas-Mail sequence if it does not converge. This immediately furnishes compactness at quantized energy intervals where the so-called problem at infinity plays a role. So the so-called problem at infinity, in this case, since V approaches infinity, is going to be this autonomous problem, non-local term, and the V infinity constant here. This has been studied. A review of all the results about this are in this work of Morros van Schaftingen, where they gather all the information, gave more information about the positive ground state solution. Okay, the autonomous problem and uniqueness of positive solutions. Because we are trying to see if we find solutions for a potential which is coming from above, and we are trying to avoid some symmetry, we are going to need some uniqueness information. This is classical when you try to approach Schrödinger equations, for example. This happens here again. Existence of positive solutions to this autonomous problem goes back to Lieb and Lyons, and these results have been extended by Morros and van Schaftingen, the autonomous case. The autonomous problem has a positive radially symmetric least action solution in C2 for any P in that range that I talked about Hardy-Littlewood inequality, Sobolev inequality. So existence is no problem, it's positive, it's radial. But what about uniqueness? Uniqueness property is known up to now for P equals to 2, alpha equals to 2, and dimensions 3, 4, and 5. So it's still a big open problem. Find uniqueness of the autonomous Choquard equation for higher dimensions and for other P's, not 2 and alpha not 2. But since the physical problem is P2 alpha 2, we decided to face the physical problem and see if we can get other results. But still, the uniqueness is a big challenge in studying Choquard equation. So what we got was the existence result when V is a variable potential. For alpha equals to 2 and P equals to 2 and N 3, 4, or 5, because then we have uniqueness of the ground state solution of the autonomous problem. And V under some hypotheses that I'm going to list and to present now, we also have positive solutions for the variable Choquard equation. So what are the conditions in these potentials that we were able to present in order to regain some positive solution? Okay, in order to go to this V infinity limit, it has to decay with some power term times exponential decay, and you can have, in our approach, either some exponential decay greater or faster than 2 square root of infinity, or if you have an exponential decay of type 2 square root of infinity, which is related to the decay of the ground state solution, then you have to have some constraint, which I'm not going to detail now, it's just some constraints in the power term. But this is basically optimal in terms of the decay you can have as v goes to infinity. So it can come from above, from below, oscillating, but it has to have some special decay in order to regain a solution. These are optimal decays, and let's see what we had to do in order to get this solution. Okay, a review on this type of results, okay, when the potential is variable, is the result of Klepp and Salazar, 2013. They got existence of positive and sign-changing solutions, assuming some symmetry on the potential. This is a result of Monica with Dora, which is very important when studying variable potentials. Then there were results of Cingolani, Klepp, and Secchi, 2012, where they also used symmetries to obtain solutions for the Choquard, in this case with a magnetic nonlinear term. What happens if you assume symmetry? If you assume symmetry on the potential V, then you have the properties of the potential. This is going to give critical points in the function with symmetry. Then you minimize the functional on a symmetric Nehari manifold. So, assuming symmetry, you can do this in this scenario of symmetric functions, and then recover some compactness. Symmetry increases the least action level, allowing to construct Palais-Mail sequence, which is also a minimizing one, but in higher levels on a problem constrained to Nehari symmetric. So that's an idea of what we found, what is interesting in these works. So you have a symmetric minimizing level, which lies in a range where compactness properties hold. The idea is to, as they do there, good candidates are found where suitable translations of the ground state solution in points that are far away from each other, preserving the symmetry of the problem. So you sum this kind of bumps, and then when they are far away, you can estimate the interaction between them, and then you can lower the level of energy in order to find or to be with a PS sequence in the range where Palais-Mail symmetric holds. The idea is pretty much this. The functional decay property of omega, which is the ground state positive solution of the autonomous problem, is required. Nonlinear Schrödinger equations, for nonlinear Schrödinger equations, for example, exponential decay plays a crucial role. In the case of autonomous Choquard, it depends on P. When P is greater or equal to 2, and that's the range of P's where Klepp Salazar worked, and there they get the exponential type decay, existence results with symmetry solutions are obtained. When P is less than 2, one sees that real non-locality feature of autonomous Choquard, as the nonlinearity in this case is not focusing enough. And then the decay of omega is not exponential, but plays a polynomial type interaction. But in the presentation today, I'm going to talk just about P equals to 2. So this is for another chapter of results. So we crucially depends on how the ground state decays. So I review here the results of Moroz's-van Schaftingen for P equals to 2. They have that if let W be a least action solution of the autonomous problem, then for alpha between n minus 4, the integer part, and n minus 1, it results the least action solution decays with this power of x decay and this exponential decay. If alpha is equals to n minus 1, then the ground state solution decays with this power of polynomial decay and this exponential decay. So that's where our estimates are going to be very tight. We use not only the exponential decay, but we also got some information or stick to the polynomial decay in order to get the best decays for the, let's say, the variable potential. And as usual, as most of you know, when trying to find critical points, we can restrict ourselves to the Nehari manifold, find the infimum on the Nehari, and this is going to give a critical point for the action functional, therefore a solution for the Choquard equation. So this is the classical setup. Twice differentiability holds when p is greater or equal to 2, and then the Nehari manifold is fine, is C1, but it does not hold when p is less than 2, so you have to be a little more careful. In this case, we are talking today, p is equal to 2, so we are fine. The Nehari manifold is smooth enough. And then, associated to the problem, there is the problem at infinity, which is basically the same problem, but v is not variable, v is v infinity, a constant. You have the infimum here, and all happens. Okay, what are the challenges or the difficulties when facing this problem? Looking for a positive solution when v is variable, we have naturally requires a comparison with p infinity. For instance, v approaches from below, which is Pierre and Liliane, or from above is one kind of approach. The approach we are doing is not from above, not from below, it's oscillating, for example, so we need some uniqueness results in order to get some range where PS condition holds. And this is possible only for these constants, as I talked in the beginning, for the physical problem in dimension 3, 4, and 5. Show PS sequence lies in the action level where some compactness property hold, perform with this uniqueness, we can show this, perform a careful comparison between the asymptotic decay of the solution and the asymptotic decay of the potential. This is very well known for Schrödinger equation, and then we developed some for the non-local term and how it behaves. As we do in these cases, the big thing is to find candidates, since we are not going to have a ground state as in the autonomous problem, try to find candidates in order to get a PS sequence and then find the limit. The threshold is given by the interaction of two copies of the ground state translated very far away. This is a copy of the ground state translated to RZI, and here you have the interaction of these terms. But this time, when we are in the Schrödinger equation, this is just a local term. Here it's a non-local term, and then you have to evaluate how they interact, even spreading out with this non-local term here. But anyways, we were able to get that this interaction is basically of this size. It's exponential to the 2 square root of infinity times potential term r to the minus n minus 1 over 2 when alpha is less than n minus 1. And it's of this value exponential times potential, power of R, if alpha is n minus 1. So this is going to guide everything that we have to do, because all the terms have to be compared with this threshold in order to see in which level we are in when taking a Palais-Mail sequence. Okay. Crucial estimate is then to see what is the role played by the potential. And then we were able to work in our problem for n in these ranges that we are working with in the following sense. If this continues, tends to V infinity with this kind of decay, where sigma is in these four possibilities of the theorem that I didn't repeat here, but it's those four possibilities, exponential very fast or exponential of the same type of epsilon r, and then you have a term here that can compensate. Then we are able to prove that the interaction of the potential term with copies of the ground state translated far away is of small order. So this is crucial because then you are able, with this estimate, you are able to estimate the energy of these bumps, two bumps that we created, and see that this term does not define the sign of, or the difference of the energy level and the energy level at infinity. So this is going to be a small order term, which compared to epsilon r is not going to play an important role, let's say. And what about the nonlinearity? This time we have a nonlinearity which has a convolution term. So at some point we have to see how the copies of two bumps are affecting the convolution term. Even if they are far, far away from each other, what happens about this convolution? Does it help the interaction to change in some sense? So we're able to evaluate this interaction and see that basically what you are seeing here in the convolution of this sum is there is a piece which is important on the first bump. There is a second piece which is important in the second bump. And then there is this epsilon r term. Basically, the difference is this small or epsilon r term plus small order epsilon r terms. So this difference is going to play an important role at the end to see how the energy is going up or down depending on this interaction. Finally, what do we do? The whole idea, as most people know now, because it has become very standard when trying to find this kind of solutions, is take a convex combination of these two bumps put very far, far away from the origin. Project them on the Nehari manifold. In order to project them, since we are using just powers, it's a homogeneous problem in some sense, although it's not really homogeneous because of the convolution. You get, this is the t that multiplied by the u function or the key function here, this convex combination. This is the t that projects the function on Nehari. And then we prove that if we are working with this key two bumps, the t's are bounded uniformly as r goes to infinity. So this is important at the very end estimates. And this is the core of solving a problem on these paths. The idea is, Project this convex combination of two bumps in the Nehari. Look at the energy and see if it's below 2 copies of the energy of the autonomous problem, the ground state level of the autonomous problem. If this is below, then you are going to be in a range where Palais-Mail works fine. More than this, you have to see if one bump is below some infinity level, which is the ground state level of the autonomous problem, plus something very small. So we have these two estimates. This is a core estimate. I'm not going to go into the details here, but that's when you see how the V potential can be, what decay, best decays it can be in order to still have some subtraction of the 2 copies of the energy in order to be in a range where Palais-Mail holds, okay? So I'm not going to give the details, but it's where we used very much the interaction between the potential and the copies of the ground state far away from the origin. And then you introduce also classical argument, a barycenter function, and then you calculate the barycenter of functions in this action level below C infinity plus alpha. And then we are able to prove that below this level and projected on the Nehari, the barycenter is different from Z1, which is the center of the ball that we are putting in the beginning, the combination of two bumps. So this is the end of the proof. What do we do in this case after all these estimates? You start with a ball centered in Z1 with radius 2 from, and then you have the boundary of this disk. For each y, which is a combination, a convex combination of these 2 points, of course, you create a function key or u of lambda r with a bump at rz1 and a bump at rz2. So you have a convex combination of 2 copies of the ground state solution. Project these 2 copies, okay, summed copies, on the Nehari manifold. If the R is far, far away, and if the V potential has that kind of decay, even if it comes oscillating to the infinity, we are able to prove that the energy is below 2C infinity. It's like 2C infinity minus something. So you know where these copies are ending up. They are ending below this energy. Suppose there is no critical point below this energy. So you can deform on the Nehari set and end up with a function with these 2 copies projected on Nehari deformed in a level C infinity plus alpha. But at this level, we're able to prove that the barycenter minus Z1 or is different from Z1, or this difference is not 0. So take this point in Rn and divide it by the modulus. Since you can divide because this is not 0, you are getting a point in Rn on the boundary of the ball. So if you compose all this, it's a continuous function which retracts this disk on the boundary of this disk. And this is impossible by Brouwer fixed point theorem. So you cannot have a retract, a continuous retract. What happened then is that when you did this deformation, it was not possible. So there is a critical point, and then you find a critical point for a problem like this in this level. all the estimates are not shown, but are crucial in order to get all these compositions. And I thank you for your attention.